So in Chapter 4, so far we've looked at general properties of aqueous solutions. We've looked at precipitation reactions. We've looked at acid-base reactions and writing those, both of these the ionic and net ionic equations. And now we're here in section 4.4 where we're going to learn about a type of reaction called oxidation reduction, aka redox reactions. So Chapter 4 classifies most reactions in three broad categories: precipitation, acid-base, and redox. Redox probably has the largest number of reactions in the world, but of these three classifications it does for sure. And we're going to spend a significant amount of time learning about how to determine if things are one of these three types of reactions, especially if it's redox. And that's the one you should always start with, since they're usually the most popular. So here we go, section 4.4, oxidation reduction reactions. Make sure you have your notebook, pencil, and periodic table out, and you can follow along and take down these notes. First of all, oxidation reductions are also known as redox reaction. Red from reduction, ox from oxidation. Oxidation is defined as the loss of electrons, aka E- symbolizes electrons. Reduction is the gain of electrons, and when you gain an E-, remember that an E- has a -1 charge to it. And so a good way to remember this, one of many, is that oxidation is loss, and the loss of a -1 thing gives you a positive charge, and reduction is gain, oil rig, and if you gain a -1 thing, you become negative. That is usually confusing. Another way to remember this is Leo the lion goes grr, and loss of electrons is oxidation. Loss of an E- makes you positive because minus is plus, and gain of electrons is reduction. So when you gain a -1 thing, you become negative. My favorite way to remember it is up and oxidation both start with vowels, and so if you oxidize something, you lose a -1 thing and you go up in charge, or you become more positive. So up and oxidation both start with vowels. Reduction and down both start with consonants, and if you gain a negative thing as in reduction, then you become more negative and you go down in charge. So how do we determine if things gain or lose electrons? Well, we use these rules to determine it, and these rules are called oxidation number rules. Oxidation number rules are a set of criteria that we use to determine the charges, or the plus or minusness, of a particular atom, either by itself or in a compound. Many times we learned a lot of these already. On the periodic table, we learned that group 1 is almost always +1, group 2 is +2, the aluminum group is +3, zinc is +2, cadmium is +2, and silver is +1. These charges are also known as oxidation numbers, and if you have these memorized, you're part of the way there in being able to assign oxidation numbers. So here are the 4 rules, with several parts to each rule, for assigning oxidation numbers. Rule number 1 is that this sort of usually correct is these on the periodic table, because some of these rules over here, like -1, -2, -3, they don't always apply. Rule number 1, back to the rules. The rules for assigning oxidation numbers is that if a substance is in its elemental form, its oxidation number is 0. So silver in its elemental form is written as Ag. It would have an oxidation number of 0. Chlorine in its elemental form is diatomic, because remember it's one of the sneaky 7 on the periodic table. So it would have an oxidation number of 0. Oxidation numbers or charges are usually written in the upper right hand corner. of the element or the species or the polyatomic ion. If there's nothing written there, it's assumed that it's 0. So here are two examples of things that are 0 when they're in their elemental form. If something is a monatomic ion, then it is its charge. And you can look on the periodic table for the metals for this. Sodium's +1, calcium's +2, as we said, zinc, cadmium, and silver, +2, +2, +1, aluminum's +3. And so if it's written with a little charge in the upper right-hand corner, it is known as a monatomic ion. The prefix mono meaning one, atomic meaning one atom, so one atom ions. So sulfur would be -2 in this particular instance. So sodium would be +1 because it has a little +1 up above it. Rule number 3 is for nonmetals on the periodic table. Nonmetal number 1 is fluorine. There aren't many alwayses in chemistry, but this is one. Fluorine is always -1 when combined with something else. Don't let this get confused, though. If fluorine is in its elemental form, F2, then it has an oxidation number of 0. But if fluorine is combined with something else, like is in KF, then fluorine would be -1, and of course potassium is in group 1, so it would be +1. Those would be their charges or their oxidation numbers, and fluorine is always -1 when it's combined with something else. Oxygen is almost always -2, 98% of the time, except when it's in its polyatomic ion form called peroxide. Peroxide you can find on the back here, O2 - 2. In this case, each atom inside of this periodic table is -1, and so its oxidation number inside of here for each oxygen atom is -1. A common compound that peroxide shows up in is something called hydrogen peroxide. That's the non-technical name of H2O2, and here oxygen would have an oxidation number of -1. The third nonmetal is hydrogen. Hydrogen is +1 with nonmetals, and it's -1 with metals. So if you see H2S, you can know that hydrogen is +1 because it's with a nonmetal, sulfur right here, because it's on the right side of the periodic table. H with a metal, like NaH, now would have to be -1. And remember, sodium's a metal, and so sodium would be +1, and hydrogen would be the -1 species. Last rule, rule number 4, is called the sum rule. These are the add them together and make a good guess. The add them together and make a good guess rule. So they have to add together to equal the overall charge of the species. So what does this mean? Say we have H3O+. This is a polyatomic ion known as the hydronium ion. Using our rules, we know that hydrogen is going to be +1 with nonmetals. There are 3 of them, and I know that whatever hydrogen is has to add together with whatever oxygen is to equal this charge in the upper right-hand corner. And since the charge is +1, it would have to add up and equal +1. And so oxygen would be -2, which makes sense because oxygen is almost always -2, as we learned right down here. But we can use this sum rule to add together to find things that are a little bit more difficult sometimes. For example, what is nitrogen's charge in HNO3? Now, if there's no number written in the upper right-hand corner, remember the number is 0, and so I know that whatever hydrogen's charge is, plus whatever nitrogen's charge is, plus whatever 3 times oxygen's charge is going to have to equal 0. Where did the 3 come from? Well, it was this subscript right down here because there are 3 of these oxygens. Hydrogen's rule, of course, is hydrogen's +1 with nonmetals. So I can put +1 in here. I don't know for sure what nitrogen is. I could make a guess, but I don't know for sure because there's no rule for it. Oxygen is always -2, except when it's in H2O2, and it's not in H2O2, so it's -2. And now I can do some algebra to figure out what nitrogen is. This is going to be -6. This is +1. Well, that means nitrogen must be +5, and nitrogen is +5 in HNO3. You may be mad about this because on your periodic table you have -3, -2, -1 written, and you're looking above nitrogen and you're like, it's charged, its oxidation number is always -3. Well, it usually is when it's with metals. In this case, it's with a bunch of nonmetals, and therefore it has a different charge or a different oxidation number, and you have to figure it out using these 4 rules. So let's do a few more examples. Here's a bunch of them in a row. H2S, hydrogen. The rule is hydrogen is +1 with nonmetals. There's 2 of them. Sulfur has to be some number, and it has to equal 0 because there's no number written in the upper right-hand corner here, and so therefore sulfur must be -2. So hydrogen's +1, sulfur's -2. Assign the oxidation number for S8. Well, you might not know this, but one of the allotropes of sulfur is that sulfur exists as a octatomic molecule, and so this is sulfur's natural state, and so its oxidation number is 0. Just like if I wrote down F2 or Cl2 or I2, all of those oxidation numbers would be 0. Same as if I just wrote down an element of iron, oxidation number of 0, charge of 0 when it's written in its elemental form. SCl2. Here I need to make a good educated guess because I don't know sulfur, and chlorine is usually -1, and I'm going to make that be my educated guess. And so I'm going to say that chlorine's -1, and there are 2 of them, and I know it needs to add together to equal 0 because there's no number in the upper right-hand corner. So that means sulfur must be +2. And it turns out chlorine's -1, sulfur's +2. Very possible. Let's find these 3 in this whole formula. Notice it adds up to 0, so using the sum rule right away, I could write myself an equation and saying 2 times sodium plus sulfur plus 3 times oxygen is going to equal 0. So sodium in this case is pretty well known to be +1 because it's in group 1, and the metals are almost always that. So +1 right here. Sulfur, I don't know, so I'm going to leave that blank. And oxygen, well, oxygen is with not in H2O2, so it's always -2. And now I can add these together. I would have -6, +2. That would mean sulfur would be +4 in this case. Another way to figure this one out is just to notice that I have a polyatomic ion in here. And the polyatomic ion I can find on the back of the periodic table is sulfite, and it's SO3 -2. So this species itself is -2, which means that sodium must be +2 because it adds up to 0. And then I could break it up and just say that oxygen times 3 plus sulfur has to equal -2. Well, it still ends up being 4, and so I break it up into the polyatomic ion if that's easier. The last one, SO4 -2. So I know that this is going to have to add up and equal -2 because that's in the upper right-hand corner. Oxygen is -2, and there's 4 of them. And then sulfur must equal something, so it must be +6 in this case to equal -2. That's assigning oxidation numbers and using the oxidation number rules. I'm going to leave these rules sit out here because now we're going to use these oxidation number assigning strategies to answer the question, redox reaction or not. Because if you remember from the very beginning of this video cast, I talked about how there are 3 different types of categories of reactions in this chapter. Well, the easiest one to determine is redox reactions, because you go through and do this process of assigning oxidation numbers, and if they change, it's redox. If they don't change, well, then it's one of these 2. And so the step to answering this question, redox reaction or not, or just a more general question, what kind of reaction is this, is to assign oxidation numbers first, and then you can decide what kind of reaction it is. So here's my first example. O2 plus 4Na goes to 2Na2O. Now, when you're assigning oxidation numbers in an equation, always ignore the coefficients. Always ignore the coefficients. Always ignore the coefficients. They don't have anything to do with assigning the oxidation numbers. Let's go through the strategy just like we did. This is an element in its elemental form, O2, so this has an oxidation number of 0. I know you're saying oxygen is -2. That's only when it's combined with something else. Here it's in its elemental form. Sodium, oh, this is in its elemental form as well, so it has an oxidation number of 0. Over here on this side, they're combined, and I know that oxygen is -2 because oxygen is always almost -2. And sodium is in group 1, and group 1 is always +1. So, have they changed from one side to the other? Yes, sodium went from 0 to +1. It went up in charge, and therefore it is oxidized. And oxygen went from 0 to -2. It went down in charge, therefore it is reduced. That's why I like the definition for oxidation reduction of being up is oxidized, down is reduced. Because if you see it goes up in charge from one side to the other, you know that it's oxidized. If you see that it goes down in charge from 0 to -2, then you know it's reduced. Let's do a second example of redox reaction or not. Let's assign oxidation numbers to this very big scary equation. Chlorine is -1. -1. Potassium is in group 1, +1. Over here on this side, it might be a little trickier until you recognize, oh yeah, this is a polyatomic ion that I memorized, nitrate right here, and nitrate has a -1 charge. There happen to be 2 of them in this formula. I know it has to add up to 0 because there's no number in the upper right-hand corner. And then what does lead's charge have to be? Oh, it's got to be +2. You can do that? Yes, you can. You can use this whole species and its charge to help determine another charge. It's another use of the sum rule that we learned about. Now, if you notice, nitrate, or whatever polyatomic ion it is on both sides of the reaction, then never bother to break it up and determine the oxidation number of each specific individual element, because you know they're the same on both sides. And if your question is only redox reaction or not what is the oxidation number of every single little species in here, it saves you a whole bunch of time. Because I know over here nitrate is also -1, just like nitrate's -1 here, which means potassium must be +1, lead's -1 because it's in group 17 right here. I'm sorry, chlorine is -1, and then lead is +2. So, did anything change from this side to this side, from this side to this side, from here to here, here to here? No changes. It is not a redox reaction because there was no change in the charges from one side to the other. Now the question comes, is it acid-base or is it precipitation? And once you become a little bit more savvy in this area, you recognize right away that, oh, lead chloride is formed. That's a soluble, that's a solid, that's a precipitate, and so it's a precipitation type of reaction. Next one, let's assign oxidation numbers in this and determine what type of reaction it is. Hydrogen, +1. Chlorate, I recognize this on both sides. It's a polyatomic ion I memorized, so it's -1 on both sides. Sodium's in group 1, so it's +1. Group 1 on the periodic table. Make sure you've got that in front of you. Sodium's group 1, +1. Let's see, OH, yeah, that's on both sides, here and here. That's why we write water that way sometimes. -1 here, -1 here, +1 here, +1 here for a hydrogen because it's with nonmetals. Look at that, nothing changed. So it is not a redox reaction. What kind of reaction is this? Well, savvy students probably already recognize that this is a strong acid, hyperhicl-high, honohiclo, and then this is NaOH, which is a strong base. And so it is an acid-base reaction, which is also known as a neutralization reaction. It makes water and a salt. How about this one? Last one we'll do. Aluminum right here has a 0 oxidation number because it's by itself. Iodine right here has a 0 oxidation number because it's by itself. Aluminum over here has a positive 3 charge because it says plus 3 in the upper right hand corner. That's a monatomic ion. And iodine right here is minus 1 because it has a minus 1 in the upper right hand corner. Notice throughout all of these I ignored the coefficients and I didn't pay any attention to them when assigning oxidation numbers. I just looked at the species and applied the rules. Notice oxygen went from aluminum went from 0 to positive 3. It went up in charge, therefore it's oxidized. Iodine went from 0 to minus 1. It went down in charge, therefore it is reduced. You can quit now, or if you want to watch the last reaction, you can. It's a bonus one. This one's tricky and difficult. Iodine 0 on this side. Always look for the ones that are easy first. Oxygen minus 2, oxygen minus 2, oxygen minus 2, because the rules say oxygen's always minus 2 and there's no H2O2 in here. That means carbon right here must be plus 2. Remember to ignore the coefficients because they have to add up and equal 0. Over here that must mean carbon is positive 4 because this is negative 2 times 2. And over here on this side, this one's tricky. I'm going to have to write an equation for this. Negative 2 times 5 is equal to 0 plus 2 times some number. Oh, that means iodine must be positive 5 on this side. So what was oxidized and what was reduced? Well, iodine went from positive 5 to 0, so it went down in charge, so it was reduced. And carbon went from positive 2 to positive 4. It went up in charge, therefore it was oxidized. Good luck with your redox reactions.